Hello everyone, my name is Paul James and I'm here to discuss my benchmark findings in visual transformers that are related to my project, uh, Uganda Computer Graphics-Based Diagnostic and Skincare Simulation Platform. So without wasting any further, let's dive into this by beginning with the reflection. So the theme and reflection, our unifying theme is the synthesis of efficiency and precision for equitable AI. Now, the overarching theme across all benchmarks is the critical pursuit of efficiency, that is to deal with the computationally data and parametric to achieve high fidelity precision in visual understanding and generation. This is not merely for performance gains, but to overcome the fundamental limitations, context length, data bias, hardware constraints, and training bottlenecks that have historically made advanced AI inaccessible for specialized global applications like dermatology, which is our project. Now, the reflection is this analysis is profoundly validating. It reflects a clear industry shift towards the exact principles that underpin our project's mission. For example, to deal with the technical problem, the explicit discussion of skin tone bias in the ViT paper moves this issue from ethical consideration to that is the first paper that we are going to talk of. And then the next paper is going to talk of efficiency is a prerequisite for equity. That is the techniques like parametric efficiency adaptation in Calico, which is a paper that we are going to talk about. And then the context compression in the video XL are not optional optimizations. They are essential requirements for building tools that are truly accessible in low resource environments. Since we are going to run ours on devices that are actually having as low as 2 GB ROM. So for the interactiveness, and then at interactive and spatial, we are going to use ISEC paper and then DefLog paper, which we are going to see down. And then this one does not actually just suggests that our benchmark is feasible. It confirms that it is the forefront of applied AI research aligning technical excellency with uh, tangible human impact. So let's dive into this. To begin with is the long video, which is the video XL compression. And then here, their abstract was talking about the video XL overcoming the context length limitation of multimodal large language models on long videos by introducing a dynamic visual summarization tokens that compress video information to sparse KVS pairs, drastically reducing computational cost while preserving the fine-grained tunes. So that is basically based on uh, the the domain problems which is going to solve the problem of MLLMs solving long videos that is leading to exorbitant computational costs and loss of critical visual information. So it is literally working on compressing the long videos and maintaining the visual uh, appearance of that video or the visual information without changing any further meaning on it. And then the core innovation is the VST model, drastically partitioning the videos into intervals, and then it starts special VS tokens to summarize that part that it has partitioned into KPS pairs and offloads original tokens, KVs. Now, implementation, how is this one related? Like, how is it necessary in my project? For example, it is going to provide the foundation for our platform to efficiently process image clips showing skin condition progressing over time or treating outcomes, ensuring medical accuracy is maintained even with high compression. And then as we are seeing here, how this one actually works, or the architecture is that, first of all, it accepts data which is either single image, multi-image, or video, and it is encoded and projected as visual tokens. Now, the visual tokens are dynamically split into intervals based on semantic consistency. And then the visual information in each interval is compressed as VSTs, KVs, which enables MLLs to perceive and understand the long inputs, then its context window. So when we move to the next one, which is, okay, this one is still talking about, this is actually showing us that it's comparing the video XL and Llama ViT, which existed. And then we are seeing a user here asking that, does this video contain adverts? We are talking of the Stripe app, this one. Does it contain adverts? And guess what? What the Llama ViT is telling us, it says that the video you provided is from a website, and it is not actually giving us what we want. And when we come to the video XL, it is telling us, yes, this video contains an advertisement that displays a black, this is which we can see it here with a light digital display. It includes various details about the product, and it's presented with colorful backgrounds, as we can see, colorful backgrounds. So literally, this one is telling us that the video XL is very accurate in identifying and compressing. So it is going to bring out, it is going to maintain the visual information, okay? And it will compress that video for us. And furthermore, uh, we go to the skin cancer segmentation and classification using vision transformers for automatic analysis in dermoscope-based non-invasive digital systems. And when we deal with this, first of all, there are domain-specific problems that global health crisis, that is skin cancer, is a significant increase high concern with steadily rising from 1992 to 2019 more than people globally die of. It is actually telling us that the limitations of the traditional, that is the it was time consuming, costly, and painful. Okay, so they are trying to solve all these problems that they are seeing. And how is this one actually relevant without, when we talk of the direct relevance, it directly validates our project's core technical stack, that is using the UNet and ViT pipeline. Its IHS benchmarks 96%, strongly supports our target of it is 96%, its benchmark 96%. So that means this is going to actually support our target, which is 85% accuracy on the Uganda dataset, Uganda skincare dataset or skin care database dataset. And it is explicit of skin tone bias fully affirms our mission to develop unbiased AI for darker skins. So as we are seeing here, the segmentation stage, the image is uploaded, detected, and segmented. Okay, then mask. After masking, it produces our binary mask, and that is what we are. It is going to type, put them into type. Like for example, here we are going to binning and then maling, malignance. Yeah, that is actually a word in their project. So the classification part comes down here, classifying the skin or the skin detected into its own parts that will be produced at the end, and then or into its multi-layer perception. Yeah. So that is now for this paper. Now the next paper is deep locks. Okay. Now when we deal with deep locks, first of all, their main problem is existing methods fail to reconstruct a wide variety of complex hairstyles. Okay. Now they are introducing this deep locks, which is going to use the synthetic data, the 4K hairstyles that were generated with Blender, and then the core model is conditional scalp diffusion. It generates a sculpture texture map where each pixel is a latent code for a hair strand. Okay. Now the conditioning is Dino V2. They are using Dino V2 features from the input image to guide the diffusion process. Okay. As we can see it from the diagram here, the first one here, we are now inputting the image, and when we input the image, it is going to use the Dino V2 features on it, and then after using the Dino V2, it is going now to direct it to the diffusion model, of which here it is now going to be converted to a scalp texture mapping, which is this one dealing here. And then from there, we are going to have what we call strand decoder, and the strand decoder is here. Okay. Now this one is going to decode, and then it is going to give us the full 3D air with everything that is not missing with curly. It is going to bring it out. Even Afro, it will still bring it out the same way. Yeah, and then how is it relevant to what? It enables the creation of culturally relevant 3D avatars with diverse Afro and Kali hairstyles, and its synthetic data generation pipeline is a blueprint for augmenting our skin condition dataset. And then its real-time usability aligns with our 3D dot. Yeah, now when we come to Calico, okay? When we come to Calico here, Calico is dealing with the domain problem of LVLMs lacking fine grain, consistent understanding of object parts. For example, the legs. So now this one is just going to tell us that when we are using this image, when we are viewing these images in 3D or in large vision transformers, it should be able to identify parts. And I actually picked this paper because I was thinking of going to use it in a way that when we are taking the picture of the part that we need to analyze, be it the leg, will our system identify that this is a leg, and then it will show us within our 3D where the leg is, and then maps it there, and then we can now view it. So that is why I picked this one here. And they use the computational architecture, which deals with the frozen encoders, which, sorry, yeah, which here, frozen encoders dealing with this part first, and then that is the segmented correspondent, and then the large, large language model backbone, that is the vicuna augmented with parametric efficiency adapters, that is here. Okay, and then when we go with the output part, which is this one here. So the diagram, it is going to tell us that image A, when we deal with the image A, okay, image A and image B, which we are dealing here, image A and image B, and then we are going to use the Everclip or Dino V2, which is going to be here, okay? This is Everclip. So it is going to be put into Everclip where it will do the queries and Q format, whatever it is. So from there, it is going to take us to LLM adapters with. So here we come to it here, and then we segment the tokens, okay, using the sum encoder and then sum decoder, okay. So it is going to put them into tokens like this. So the image show, it is the output text will be like the image shows a dog, that is the segment one, and then segment two, the unique parts are the neck, segment one, and then the leg, segment two, the foot, segment two also, the body, and then the tail. So it is actually telling us that from the two images styles, identify all those parts. So that is why it is actually irrelevant to this, to our project. And when we go to ISEC, now this is the interactive segmentation and manipulation of 3D, whereby we can manipulate 3D to change, because we are talking of skin biasness here, how to create the 3D with uh, dark skin, okay? So this is why I came in here with this week, whereby we can change our 3D to a dark skin part, okay? So it is, our 3D is, we can just modify it from there, okay? This is where the editing comes in, manipulation toolbox, whereby we can edit scaling, combination, coloring, and then copy and paste, and then removal, okay? Of which we shall not use most of this, but we shall use editing, colorization, scaling, and combination, and then probably copy and paste. And then the user, click, I viewer. Okay, this is actually hard to understand it here, but in theirs it is what. So from the overview, it says that this one contains two novel regions control algorithms that are well suited for scene manipulation with reliable efficiency, and then very many things come along. So the implementation relevancy, it allows for dynamic skin tone adjustment for avatars via text prompt, that is turning into a black man, and then enables precise isolation of skin lessons on the 3D avatar for high fidelity simulation, and it provides an interactive toolbox for users to explore conditional changes. Yeah, so this is how it actually works here. First of all, someone has loaded an image here, and then it is turning this image into Albert Einstein. So we are seeing Albert Einstein, but it came away from someone else. So this is why actually I pick interest in this benchmark. And then here, making someone smile. He wasn't smiling, and now we are seeing him smiling. And then furthermore, turning someone into Hulk. This one is a movie. So we are seeing him, and then we are turning him to green, and we are making some changes on him to make him like Hulk. And then finally, the part that actually attracted me is that turning him into a black man or turning his clothes into white. We are seeing here that the original one is blue. So we turn him into black man and then changing the text or the clothes to white, okay, from the original or to this color. It is just that is what actually took my mind in this benchmark. And then finally, what is the synthesis of the technical insight of this? Now, the core architecture is validated. The visual transformer and the segment anything model pipeline is proven for medical grade skin image analysis. Our choice of UNED and what is robust and performant. Now, efficiency is achievable. Techniques like the video XL is summarization tokens, and the Calico is parameter, parameter efficiency adopts 0.3%, show how to add complex functionalities, long video body part mapping without prohibitive computational cost. Now, there's also bias mitigation is central. Now, the skin cancer papers acknowledge of bias, and devlog is focused on diverse hairstyle, provide strong external validation of our own core to serve darker skin tones with unbiased uh, AI. Now, the 3D fidelity and interactivity are solved. That is the Isaacman and devlogs provide a clear pathway to achieve high fidelity, real-time 3D avatar manipulation and customization directly in a web environment. And now implementation roadmap is that we are going to implement and train the validated U, net, and V pipeline on skincare and integrate grant cards. Now the avatar simulation is going to be, we are going to use the devlog principles to generate synthetic skin data and realistic avatar styles. And then implement the Segmanis principles for precise lesson application and skin tone adjustment on Blender or 3D 3.js avatars. So now the full body expansion. We are going to integrate the Califais inspired models for automatic body part mapping from user upload to the full body avatar, and then leverage video for potential growth. So in conclusion, validated technical foundation. This benchmark exercise confirmed that our chosen architecture is at the cutting edge, with each component supported by proven state-of-the-art research. Now the clear path to unbiased, we are uniquely positioned to address a critical gap in global dermatological AI by building tools, especially for diverse skin tones, a mission directly reinforced by these papers, and then delivering a scalable platform. Now, the emphasis on efficiency, parametric efficiency, adapters, compression, real-time rendering ensures our platform will be accessible and functional even on low-resource devices common in Uganda, fulfilling our goal on equitable healthcare access. Thank you so much. I remain Paul James.